Hey, welcome back to your favorite pre-calculus class. We're going to look at complex zeros and fundamental theorem of algebra today. So let's start off with a complex polynomial function. So this you can have, now we're going to explore into, instead of just being in the real numbers, we're going to be dealing with complex numbers as well. So we're going to have complex variables, complex polynomials. So that definition there is very similar. You can read through that. You have your coefficients there simply can be complex numbers now. You still have your powers being non-negative integers, and your x's can now be complex variables. And then you have a complex zero if f of r equals 0. So simple as that. Let's go into the fundamental theorem of algebra. This is fundamental, so meaning very important to algebra. This says every complex polynomial function of degree n greater than or equal to 1 has at least one complex zero. So for instance, let's say we have f of x equals, I don't know, 2x to the 4th minus x cubed plus x minus 1 or whatever. This thing is degree 4. So this theorem states that it has at least one complex zero, at least one. Complex, meaning it may not show up on a real number graph, but it's got to at least be complex. And then this was taken even further with a corollary. And the corollary actually states that whatever the degree is, you will actually have 4 complex zeros. That's how many you will have. They might not all be real zeros, right? In other words, this 4th degree, it might not actually hit 1, 2, 3, 4, right? Because some of them might be complex. So this thing, maybe it only hits twice, has 2 zeros, and the other ones are complex. They don't show on the real number graph. Okay, so the degree, whatever the degree is, that's how many complex zeros you're actually going to have. Which takes us to the next theorem. Every complex polynomial function of degree n can be factored into n linear factors as well. So if you have n zeros, you're going to have n factors. The conjugate pairs theorem states if a plus bi is a zero, these complex zeros come in pairs. That means its complex conjugate is also a zero. So for instance, if 2 plus 3i is a zero, then its conjugate, 2 minus, you change the sign in between them, 2 minus 3i is a 0. Okay, so for example, that function might be, let's say you had f of x equals x squared minus 4x plus 13, right? And you were finding its zeros. If you had the function and you're going back to the zeros and you're like, well, this darn thing doesn't factor, forget that, so we're going to have to throw it into the quadratic formula. X equals negative b plus minus square root of b squared minus 4ac all over 2 times a. So we got 4 plus minus 16, what is that, 52 minus 52 all over 2. 16 minus 52, negative 36 all over 2. So we got 4 plus minus, this is 6i, right? The square root of a negative 36, 6i, all over 2. You divide both those by 2, and you get 2 plus or minus 3i. That's his I right there. Not a very good I. So you notice 2 plus 3i and 2 minus 3i. Both of those are the zeros for that function, x squared minus 4x plus 13. So those things come in pairs. So if you have like negative 3 minus 7i, then you know negative 3 plus 7i is also a 0. That's what this theorem is stating. So we can build polynomials then. Let's build one here. Find a polynomial function of degree 4, so we should end up with an x to the 4th here, whose coefficients are real numbers and has those zeros. 1, 1, and negative 4 plus I. So this is expecting us to know the conjugate Pier's theorem. So if negative 4 plus I is a 0, we know negative 4 minus I is also a 0. And since we have the 4 zeros now, right, you got to have 4 zeros to be a degree 4. And now we can go backwards from the zeros and build the polynomial. So if 1 is a 0, then x minus that number 1 is a factor. and you have another 0. 1 again, it repeats twice. So x minus that 1 is also a factor. You have negative 4 plus I, so x minus the negative 4 plus I, and then you have, didn't realize that was, x minus the negative 4 minus I is also a factor. Now we don't know this leading coefficient right here, this a, so we're just going to leave it as a for now. What we typically do when we build this is just let that be 1. Make it the easiest. Alright, so now we're going to FOIL that. And so we've got x squared minus x minus 2x plus 1. Here, let me distribute that before I take care of those. So we have x plus 4 minus I times x plus 4 plus I. Now I'm going to take the x through to everybody. I'm going to take the 4 through to everybody. And I'm going to take that negative I through to everybody. So we have a x squared minus 2x plus 1. I've got x squared plus 4x plus xi plus, now I take the 4 through, 4x plus 16 plus 4i. Then I take that negative I through, negative ix or negative xi minus 4i, and then negative I times positive I is negative I squared. And if you remember from working with complex numbers, I squared is negative 1. Because I was defined to be the square root of negative 1, so I squared would be negative 1. So we need to replace that I squared. Okay, so let's keep going here. X squared minus 2x plus 1. We've got x squared. There's no other x squareds. I'm combining like terms. I got 4x. I got 4x. So it looks like I got 8x. I've got xi minus xi. That's gone. I got 4i minus 4i, that's gone. I got 16, and this is a minus a negative 1 right there, so that's actually a plus 1, because I squared is negative 1, so 16 plus 1, we got 17. And then I'm going to take the x squared to everybody, I'm going to take the negative 2x to everybody, I'm going to take the 1 through to everybody. So this becomes a x to the 4th plus 8x to the 3rd plus 17x squared minus 2x to the 3rd. Oh my gosh, this gets messy. Where am I at? Minus 16x squared minus 34x. Then I take the 1 through to everybody, plus x squared plus 8x plus 17. So I've got a parentheses x to the 4th. Let's see, 8x cubed minus 2x cubed, so I got 6x cubed. I'm running out of room here. I got 17x squared minus 16x squared. That's a 1x squared plus another 1x squared. 2x squared. So that's squared right there. 2x squared. I've got a minus 34x plus 8x. That's what, 20 minus 26. X, and then I've got a plus 17 on the end there. This is what my f of x is equal to. Now again, this a right here in front, what we do is we just let that be 1 most of the time, unless they give us a point. If they gave us a point, like let's say they said f of 0 is 17, then you'd plug the 0 in for x, the 17 in for y, and you'd solve for a. And in this case, if you plug 0 in for x, 17 for y, you're going to find that a is 1 anyways, in this case. But again, a is not always 1. Here's a picture of it if your a was 1. You notice you hit the point 0, 17. Notice you have those two zeros, 1 and 1. X equals 1 with multiplicity of 2. So you're just touching right there because you've got that even multiplicity. Okay. All right, now we're going to find the complex zeros of polynomial functions. So here's a 4th degree polynomial. And what we're going to do here is I'm going to allow you to actually kind of cheat, since we've learned how to do this by hand with possible rational zeros last time. And what I mean by cheating is go ahead and take the original polynomial. And I know that you can list out your possible zeros, and then you can start testing them. But what we're going to do is we're just going to save a little time. We're going to punch it in. to Desmos, or whatever your graphing calculator is, and we're going to look for an integer 0. So you click on the graph and you notice it'll give you a gray spot and you're like, oh, it hits right here at -2. This other one right here is like 0.333 or whatever. So we're going to take the we'll take this integer at -2. So we're like, oh, well, -2 is a 0. So since -2 is a 0, if we're going to start factoring this thing, if -2 is a 0, then x minus the -2 is a factor. In other words, x plus 2. And now we've got to go to the side and do the division. So 3x to the 4th plus 5x cubed plus 20 blah, 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 divided by x plus 2. So I put the -2 in the box, do our synthetic division, 3, 5, 25, 45, -18. Bring the 3 down. 27 times 2, what's that, 54, -54, and that's what, -9, -9 times -2, 18, and 0. You should get a remainder of 0, because we know from the graph -2 is a 0, so the remainder should be 0, and then I'm going to use that for quotient, leading coefficients there, so 3x to the 1 degree less, so to the 3rd in this case, since we start out with our dividend being a 4th degree, minus 1x squared plus 27x minus 9. And then from here, you can either continue to test with your rational zeros, but I'm noticing I got 4 terms, and it looks like I can factor this one by grouping. So I take a look at those first 2, and I'm like, oh, looks like an x squared will come out of each of those, an x squared, and that leaves me with 3x minus 1. And out of those 2, I can also take a 9 out, and I'll have 3x minus 1. Notice that both of those have a 3x minus 1. So 3x minus 1 comes out, leaves me with the x squared plus 9. Again, I'm factoring by grouping. So 3x minus 1 right there. And then I try and factor that x squared plus 9, but it doesn't factor. So that darn thing, since it doesn't factor, and we're trying to write this thing in factored form. So what I'm going to do is I'm going to find the zeros, and then I'm going to create the factors from the zeros. So from here I have -2. From here I have 1/3, and if I was to solve this, x squared plus 9 equals 0. Take the 9 over, so x squared equals -9, so I have plus or minus 3i. So that means my factors would be x plus 2, 3x minus 1, and I have 3i, so x minus 3i is a factor, and -3i, x minus the -3i is also a factor. In other words, x plus 3i. Here we are in completely factored form. I should write this f of x equals. All right, there's our f in factored form, and of course all your zeros there are also listed. All right, thanks for listening. See you guys in class.